Hi, I'm Hassan, the lecturer here at the Institute of Medical Education, and today we're going to take a look at solutions to Section 3 of ACER's GAMSAT Green Booklet, Practice Test 1, specifically Unit 13, questions 49 to 51. So this unit talks about thermodynamics, it talks about how to read reaction progress and energy diagrams, and specifically how to use Arrhenius' equation to calculate the activation energy of a reaction. So before we dive into the unit, let's take a quick look at what a reaction and the thermodynamics of a reaction actually is. So if we take a look, chemical bonds in a reaction, or in the reactants, they have to be broken so that new bonds can form as products. So to achieve these bonds, the molecule has to bend into an unstable transition state, so which you can see here. So the transition state, it's a high energy state. Think about it, it's unstable. And some energy, so this is called the activation energy, must be added for the molecule to reach it. So if we take a look at these energy diagrams, we can see that reactions can either be exothermic or endothermic. So exothermic reactions release heat. And if we look at it through thermodynamics, and if we look at it through enthalpy, so enthalpy is the internal energy of a system. If we're releasing heat, we see that in exothermic reactions, they are considered, their enthalpies are less than zero because they're losing internal energy. Whereas for endothermic reactions, we're adding energy to the system. So we're adding internal energy to the system. So you can see here, we're adding energy, which means the enthalpy is going to be greater than zero. So I think it's important to note that, you don't have to know this obviously to answer the question in this unit, but in future units, in future GAMSAT questions, you might have to know what enthalpy is, entropy is, Gibbs free energy, activation energy, which we're going to go through in a second, exothermic, endothermic. You have to know in this instance, they've given you the gas constant, but how to manipulate it to using the ideal gas law and all of those sorts of questions. You just need to know them, because if you do, it makes it so much easier to answer questions like this. So if we dive right into it, for question, sorry, I jumped the gun here. Question 49, it states the activation energy is represented in figure 1 by, so we can clearly see that the activation energy is here, and in the diagram, I think it's got it here as E1, E2. So it's obviously between E1 and E2. So the answer for 49 has to be A. So if we just go now on to question 50 and 51, we have to use Arrhenius' equation to identify in question 50 or calculate the activation energy for a reaction that is, they've told us, is 10 times faster at 32 degrees than it is at 22 degrees. So straight away we know, so we're going to have to, if we look at the Arrhenius equation, what's K2, K1, T2, T1? So we know temperature 1 and K1 has to be the initial. So that's going to be, let's say temperature 1 is 22 degrees and the K1 is going to be 1. Temperature 2 is going to be 32 and K2 is going to be 10. But remember here, look closely, the gas constant which we're going to use the equation, it's represented as joules per mole per Kelvin. So we've got to convert temperature, the degrees Celsius to Kelvin. And the easiest way we do that is by adding, so to convert degrees Celsius to Kelvin, it's adding 273 to the degrees Celsius to get your Kelvin. So if we just get out our whiteboard, so I'll remove Ghostman, I'll just get the whiteboard out. Where are you? And I might want to get my brush out. Sorry, wrong one again. Toolbar. So let's just write it out. So we've got 2.303 log base 10. And we've got, so K2 is going to be 10 over 1. So K2 is 10, K1 is 1, what we discussed earlier. And it equals, so our EA over our gas constant, which is 8.31 joule mole K. So let's just write it as, 8.31 joule per mole per Kelvin times, so T2, so if we're going to do quick math, so we've got, it's 22 degrees, so 22 is 32 degrees, plus it by 273 is about 305 Kelvin, minus, so T1 is 22 plus 273 is about 295 Kelvin. So I'm going to leave the units here because I'm going to show you why it's important to leave the units. And T1 times T2, so let's say 300 times 300. So it's going to be 9 and 1, 2, 3, 4 zeros, 4K squared. Let's leave the units. So this is what we get. So now we just have to solve this equation to get our answer. So let's work with some numbers that are easy to work with. So 2.303, I don't like working that. It's too many decimals and it's all over the place. So let's just round it up to 2.5. So it's going to be 2.5 times, now remember, log 10, so that's log 10, equals 1. So it's just going to be 2.5 times 1. So the answer is going to be, left-hand side is going to be 2.5. The right-hand side is going to be, so we've got all of these values. So the 8.31, let's just make it 8. I don't like working with 8.31. So if we make that 8, but I mean, I don't want to use this. So let's make this 8, but let's chuck it onto this side. So times this, all of this by 8. So if we times 2.5 by 8, it's going to be about 20. So let's just say 20. Easier again to work with 20. So actually, let me just change this. So to 20. So 20 equals, remember, let's leave the units. So it's going to be EA over, remember, it's still going to be joule mole per Kelvin. This is going to be 10 over 90,000. So let's just simplify that. So 10 Kelvin over 90,000 Kelvin squared can be the same as 1 over 9,000. So the reason why I want us to leave the units here, I'm being a bit anal about this, is because the way that the answer is represented here is technically incorrect. So it should be, if we go through the motions here, let's bring this Kelvin up here because it's divided. So it will be EA, say Kelvin over joule per mole. So it's going to be times 1. So that times 1 is just going to be the same. So that's going to be 9,000. Yep. But you can see here that because this K came up, this K came across, so it would be K squared. So if we times that, so K times K, so K squared over K squared, we can remove the 2 kelvins, and we're left with 20 equals EA over 9,000 joule per mole. We move it across, it's going to be 18,000 joule per mole equals our activation energy. So therefore it's about, if we divide it by 1,000 to make it kilojoules, 180 kilojoules per mole. So this is why I was being very pedantic about the units. It's represented in your answer in question 50 as either kilojoules or joules, but technically speaking, the activation energy is in kilojoules per mole. So if we go here now and we go back to our answer 50, actually I'll remove our whiteboard here, just go back here, hide our whiteboard. So answer 50 equals D. So it's going to equal 200 kilojoules. It's approximation. We did a lot of approximation. You could have used other numbers, but as long as you get to around that number, you'll be fine. So now let's move on to question 51. So if I just hide the screen brush here. So question 51, again, we have to use Arrhenius' equation. It's asking, and I guess it's telling us that the rate of reaction increases by a factor of 10 when the temperature increases by 3 degrees. And For a larger temperature increase, the rate of the same reaction is a factor of 100. So let's just get our whiteboard out again. And let's draw this. So let's write the first equation. So the first equation is going to be, remember, it's going to be about approximately 2.5 by log 10 to the power of, it's telling you the first reaction is a factor of 10 over 1, which equals our activation energy over our gas constant. And we know that the temperature difference, which tell us the increase in temperature, is 3 degrees Celsius. We don't have to convert it to Kelvin in this instance because the answers are represented in degrees Celsius. So just to save you time in the GAMSAT, it's fine to leave it as just Celsius because the answer is in Celsius. So we'll leave it at that over T1, T2. So that can be our equation 1. So equation 2, we're told 100-fold increase. What's the temperature change going to be? So if we go 2.5 times log 10 100-fold, it equals activation energy of our gas constant, our X, we don't know what the temperature is, that's what we're trying to find out, T1, T2, that's our second equation. So you can see here, remember logarithmic scales. Log 10 equals 1, log 100 equals 2. So that means the left-hand side over here is going to equal, so let's write for both sides. This left-hand side, 2.5 times 1 is 2.5. This left-hand side is going to be 2.5 times 2, which is 5. So can you see now that equation 2, left-hand side, is double equation 1, left-hand side, which means equation 2, right-hand side, has to be double equation 1, right-hand side. Therefore, the temperature has to be 6 degrees because 3 times 2 equals 6 because it's double. So it's twofold. If we go back now, I just hide the screen brush here. If we go back, the answer to question 51 has to be A. So it's going to be 6 degrees. Now, if you do have any questions about this unit, you can post them in the comment section below. However, with these type of chemistry, I employ all of you to go back, brush up on your thermodynamics, brush up on how you can read equations, just simple arithmetic. Please use and leave all of your units in practicing. Obviously, in the GAMSAT, you don't have to because you want to save time. But if you're practicing, you're still in the practicing stage, leave the units because if you didn't, you would have been confused with question 50 and thought that activation energy is represented as just kilojoules or joules. It's actually kilojoules per mole. And if you didn't practice this way, you might get questions in the GAMSAT that need you to manipulate and these types of equations, and they won't tell you in the stimulus, give you some background information, and you have to use it from background knowledge. So make sure you leave all the units, you be systematic, you understand your thermodynamics, and you should be fine. If you do want to contact us directly for more help, please do so. We'd love to help. Thanks for your time. Bye now.